Okay, let's proceed.
Good evening, everyone. Welcome to the Centenary Celebration of the Department of Mechanical Engineering, IIEST Shibpur. Today we are here for the 30th lecture under the Centenary Lecture series to be delivered by our Honorable Professor Prashanta Kumar Das. Uh, this session will be chaired by Professor Bijan Kumar Mondal sir, who is who is the professor of Department of Mechanical Engineering, IISc Shibpur. Uh, the topic for today is oh wait, just a second. Okay. So the topic for today's lecture is nexus between human thermal regulation and cardiovascular operation. So this Vision Kumar sir will take away then.
Professor Mondal, please.
Am I audible?
Yes.
Okay. So thank you, Jui. So it is my pleasure to sit on a chair where Professor P.K. Das will deliver a lecture. Professor Prashanta Kumar Das is not only an excellent academician, he is also a very nice person. In fact, when I was completing my MTech at IIT Kharagpur, he joined IIT Kharagpur as a faculty member. So in that sense, okay, I may not be a direct student, but I am also a student of Professor Das. Anyway, let me formally introduce Professor Das. So he is currently Professor A.S. Davis Chair of Thermodynamics in the Department of Mechanical Engineering and ex-Dean of Postgraduate Studies and Research, IIT Kharagpur. He is well-accomplished academician. His research activities encompass diverse topics of thermofluids, then fundamental studies, applications, experiments, and analysis. His research interests include multiplex flow, phase change heat transfer, experimental techniques, and thermohydraulics of nuclear reactors. Also, he is now presently working on sensor developments, and they have developed some unique CFD code for the analysis of single flow and multi-phase flow. He has published around 230 articles, journal papers in the international journals, and has more than 10 patents to his credit now. He has conducted many funded projects and provided consultancy to different industries and government organizations. Professor Das is a recipient of the K.N. Sitaram Prize and Medal given by the Indian Society of Heat and Mass Transfer. He is also a fellow of the Indian National Academy of Engineering and the Indian National Academy of Sciences. He served as an associate editor of the Journal of Heat Transfer of ASME. He was also a participant in an academic leadership training program conducted jointly by IIT Kharagpur and the University of Cambridge, United Kingdom. Currently, Professor Das is actively interested in developing low-cost medical devices and health support systems. The electromechanical cardiovascular replicator developed by his group won the prestigious Chitari Gandhian Young Technological Innovations Award. He has guided more than 30 PhD students, and around 15 students are working under him for the PhD award. And so now I invite Professor Das to deliver his lecture on the topic nexus between human thermoregulations and cardiovascular operations on the occasions of the centenary celebration of the Mechanical Engineering Department of Indian Institute of Engineering, Science and Technology. Professor Das, take the charge. So Professor Das is requested to take the charge now.
Yeah, I am trying to share my So at the outset, very good evening to all the participants. I could means I came to know that somebody joined from USA. So good morning, and I mean it is a very different kind of a feeling because I can see very senior people who are the alumni of B College. At that time, it was B College Shibpur. They have joined, and a very senior colleague of mine. Colleague of mine means in general, I can call him a colleague, but he's like mentor of to all of us, to many of us. Professor Mollik has also joined. I mean, good afternoon to all of you. At the outset, I like to thank the organizers for giving me this opportunity to interact with the audience, which comprises of so senior persons. Now, the topic on which I am going to deliver today's lecture is nexus between human thermoregulation and cardiovascular operations. Mostly, I will tell the background, which I am also trying to learn because there are many aspects. Particularly, I will touch upon very cursorily that there are biological aspects which, being a mechanical engineer, it is difficult to understand, which will go to the chemical and biochemical domain. I will just mention that. But this is very interesting topic. Any biological topic is interesting. Any topic of life science, and particularly this is very interesting. And my interest came to this topic because of thermoregulation, which deals with heat transfer, to some extent thermodynamics, and of course fluid flow also. And as I have told that these aspects which are there in human body, or the body, for that matter, body of an animal or even plant, they are very complex. And with simple physical rule, it is very difficult to explain them. But I will try my best to share with you what I have learned or what I have understood. Now, if we see the temperature distribution of human body in a human body and temperature regulation in the human body, the methods or mechanisms of temperature regulation in human body, then one has to be little bit aware of the evolution tree. In the evolution tree, human being, they occupy almost the topmost position, and the thermoregulation has also evolved as the, I mean, from the root of the evolution tree towards the top. If we see animals, the animals of lower category, they are called ectotherm, where the temperature of their body is not controlled by them. They do not have a fixed temperature.
Sorry for interrupting, sir.
Am I audible? Is there any problem?
You're audible, sir, but can you please make it presentation mode? We are not seeing the slides.
Only first slide, I am there in the first slide. Can you see the first slide?
Yes, yes. Okay.
Okay.
Oh, you can probably make full screen then. Sorry, sir.
Okay. Okay. Is it all right?
Yes, sir. Yeah.
Okay.
Thank you.
So, as I was telling that if we see the, let's say the insects or even animals of lower category, then they are called ectotherm, where the temperature of their body is not regulated by them, but mainly by the environment. Now, everything has got its pros and cons. So when the animals, they are not regulating their body temperature, they need very less amount of energy. Their food requirement is less, but they have got limitation of their habitat. They cannot live everywhere. Whereas if we consider human being more or less throughout the year, throughout the day, they maintain some sort of a body temperature, which is uniform, and they can control the body temperature also, depending on the environmental condition and other conditions. Other conditions are physiological conditions. So this has got the advantage of temperature control or thermoregulation, but at the same time, it is very, very much energy demanding. It needs large amount of energy. But again, for the advantage, it gives lot of flexibility. Human being can reside in the Arctic region, and they can also have their physiological functions in some sort of a region where the temperature is very high, let's say desert kind of climate. So with this, I go to the next slide. And even in the textbook nowadays in class, in school, they tell that human body is a very, is very much similar to a heat engine. But what they do not tell that as a heat engine, the human body has got low efficiency, really very low efficiency. But it is a very good thermostat. As a thermostat, its performance is excellent. So how its performance is excellent because it can maintain the temperature to a very precise level. And as the temperature of human body we are talking of, there are two temperatures. One is the core temperature. The vital internal organs like heart, lung, liver, etc. They maintain this temperature very precisely. And there is skin temperature or peripheral temperature, which can vary depending on physiological action and particularly depending on the environmental condition. Here, I can show that how challenging is to maintain this temperature, because you can see there are different mechanisms of heat transfer from the external agency. There could be solar radiation, direct and diffuse. There could be conduction and convection because human being there in the atmosphere. And let's say human being is clothed like this. So you see what are the different mediums of heat transfer we are getting. That we are getting bare muscle, then fat, then skin, and then there will be some sort of air gap, and then probably this gentleman is wearing a sock, so the sock is there. After that, then again there is an air gap, and then there is some sort of trousers, and outside there is air. So, this is for a well-dressed man, but if we consider some sort of aboriginal, so his case, it will be different because this kind of socks and trousers, etc. will not be there. But whether it is a well-dressed man or some sort of person who is dwelling in a forest, so the thermoregulation will work equally efficient. And inside the body, there are also different kind of mechanisms and different factors for heat transfer, which I will explain as we proceed. So at the first slide, I like to convey, in this first slide, I like to convey the idea that human body is also acting as a very good, very excellent thermostat. And this thermostat is working 24/7, and it is working also in if the human being is moving from one part of the globe to the other. Now, I have mentioned the core temperature and skin temperature. So here I am showing the core and skin temperature. So this is the core temperature for cold ambient condition, and this is the core temperature for warm ambient condition. And core temperature, it is maintained closely at 37 degrees Celsius. Maybe a 5 degrees Celsius of difference is noticed time to time. But there are peripheral temperature varies very largely. So we can see at the hand, we can have 28 degrees Celsius, somewhere we can have 32 degrees Celsius, somewhere we can have 36 degrees Celsius. In the face, there are, I mean, within this small area, there is lot of temperature variation, 34 degree, 32 degree, 33 degree, like this. Because brain is there, and of course I will not get time to discuss that the thermoregulation or the temperature control of brain, that is again very challenging. I mean, to understanding it also it is challenging. So then this core temperature, whatever may be the ambient temperature, whether it is summer or winter, whether it is Arctic region or desert region, it remains more or less constant. So that has been done by the design of the physiological system of human being. But why to maintain core temperature? The reason is metabolism that depends on temperature, endocrinal operations, because metabolism consists of number of chemical reactions, endocrinal operation that is also dependent on number of chemical reactions. So these things are temperature dependent. Then operation of many tissues, particularly muscle tissues, these are viscoelastic material, and their function depends on the temperature. Then protection against disease and infection. A certain amount of temperature needs to be maintained inside for the protection against disease and infection. It is called febrile response. Whenever there is a disease, temperature becomes one kind of, body temperature becomes one kind of tool for activation of immunological systems and endocrinal system. So fever, when the body temperature is high, people may see that it is some sort of discomfort and some sort of disease, but it is nothing short of that. It is kind of a defense mechanism, and it will change the set point of the core temperature. That's why our body temperature will go high, and that change in core temperature setting, that will again trigger a few immunological functions and a few endocrinal functions. So that is how the body temperature is important. Now, normally, the core temperature is to be maintained at constant level by a mechanism called homeostasis. Homeo means it is equal, and then stasis, that means staying unchanged. So if there is any kind of disbalance or unbalance from the normal condition of our physiological operations or due to environmental condition, then what will happen? There will be a tendency for a change in the core temperature. And this change that will be detected by a receptor, it will go to the control center, and then there are effector, and that will operate so that this change can be made into minimum. Okay, there is minimum amount of too little imbalance, not very large imbalance, or there is no imbalance at all. In general, it is called homeostasis. It could be for anything inside the body, any kind of change inside the body. It could be a change in protein structure. It could be the balance of sodium, potassium. It could be the balance of plasma and the liquid content in the body. But it could be the change in temperature. So now let us go to the homeostasis, which occurs due to thermoregulation. So thermoregulation, we can call it a number of mechanisms that is well orchestrated by hypothalamus to maintain the homeostasis, particularly the homeostasis as far as the core temperature is concerned. So let us start somewhere here. Let's say this is our hypothalamus. It is getting some sort of signal from the cold environment, and then to tackle the situation, it is generating a few actions. One action is vasoconstriction. So the blood vessels particularly below the skin, that will get constricted, and the blood flow that will be restricted through the vessels which are just below the epidermis. So that is one, and that will give lesser amount of heat loss from the body, and body temperature will try to increase. And then there is some amount of energy release due to muscle action, which is known as shivering. There could be even goosebump, which I have not mentioned here. So due to goosebump, what happens? All the pores through which the body hairs are coming, they will get constricted. If they are constricted, there are two things. There will not be any kind of evaporation from there, or non-perceivable sweating, that will not be there. At the same time, when the body hairs are they stand erect, what will happen? That they will restrict the heat transfer from the body by producing some sort of resistance to the airflow over the body. So that is also another mechanism for conserving thermal energy, or protecting the body from losing lot of heat. Okay. If we go to the other side, this is the hypothalamus, and it is getting some sort of hot signal from the environment is now hot. So what it will have vasodilation. So the blood vessels will have now larger diameter below the skin or epidermis. So there will be good amount of heat loss, and of course there will be sweating. Sweating is a very strong method for thermoregulation when the temperature is higher compared to what is conducive for the body. There are other biological mechanisms, like it is not only protecting the body from excess heat loss, and not only promoting more heat loss during the hot condition, but it is also giving the body some sort of flexibility to acclimatize with the condition. How it is done? It is actually a chemical or biochemical process, or number of chemical and biochemical process. It is done by a number of hormones and proteins. Every cell that will contain protein, which are called heat shock protein. If there is a shock due to higher temperature or due to lower temperature, the protein structure changes, and it helps the body to get acclimatized with the changed environmental condition. Sometimes due to physiological condition also, maybe due to some drug, due to some illness, there is change in the body temperature. Fever I have already mentioned. So that also, during that time also, this shock protein or protein for the thermal shock, they helps us to acclimatize or to come in terms with the changed condition. Here, though the example is not from human body, but I like to give this example because of its uniqueness. So there are birds, etc., which are there in the region, Arctic region. So they have to walk on the icy or ice-covered ground. And obviously, this is very low temperature. And when the blood will come here, so blood will come this portion, so it will become very cold. And then if this cold blood goes back to the heart, so there will be a problem, and the thermoregulation will not be there. So what is done? The blood vessels changes very much. They make some sort of a network of very small vessel, which is comparable to our microfluidic heat exchangers. And when it is going back, so it is making some sort of a counter current heat exchanger, so that it gets heated with the incoming blood, which is coming from the heart and which is at a higher temperature, so that ultimately when the blood is going to the heart, it is not that cold. So two concepts which human being has picked up later on. One is the concept of countercurrent heat exchanger, which is very good in exchanging heat, and the concept of microfluidic heat exchanger, that is also very efficient in heat exchange between two streams, that is adopted by this physiological design. Now, another unique kind of thermoregulation process I like to show, that this is a case of frostbite. So let's say the earlier case, I have talked of a bird which is, usually expected to have the habitat in the very cold region and walk over the ice-covered ground. But let's say somebody who is not not expected to walk over the ice-covered ground and is exposed to very cold condition, then we can see that there is something called frostbite that takes place. So frostbite, it is also a method of thermal regulation or thermoregulation. What happens that if the body limb which is exposed to very cold temperature, if the blood comes over here, then blood will get cooled, and there is no internal mechanism to take care of this extreme cooling. So what will happen? The body will use, or the thermoregulation system will use these limbs as some sort of sacrificial part. So they will cut the blood supply to this limb, and ultimately there will be death of this cell, and we will know that what is frostbite. And here it is shown that it happens layer by layer, so that ultimately there is one layer where there is no effect of frostbite, but these layers gradually the blood supply is cut from there, and by sacrificing some sort of peripheral limb, one can protect the heart and the other vital organ within the body. So this is a very extreme case of thermoregulation, extreme strategy of thermoregulation in human being. Now, the thermoregulation process here, again, I am coming back to the subject. We can see the thermoregulation process, it involves other systems also. It involves cardiovascular system, respiratory system, neuromuscular system, digestive system, like this. It is mentioned here, renal system and integumentary system, which is basically the skin and the muscles just below the skin. And then subsystem that govern the human thermoregulation, we have got nervous system, then muscular system, then cardiovascular system, and respiratory system. So cardiovascular system, what we can see that it is affected by the thermoregulation, and it is also taking part in the thermoregulation. So it has got a dual role. And this kind of dual role is there for other systems also. The thermoregulation in human being, it is quite complex, but we will discuss today regarding the role of cardiovascular system, and that too we will keep our discussion at a simple level, excluding the chemical and biochemical part of it, which is also equally important. Now, nexus between the human thermoregulation and cardiovascular system. Again, I will try to draw your attention or tell you regarding the evolution. So evolution, if we can see that the heart also, not only the circulation system, but the heart structure has also grown from complex to more complex one as we climb the tree of evolution. So initially, let's say it is fish. So in fish, we have got heart of two chambers only, where the bloods are mixing. What is coming from the systemic circulation and what is coming from gill, they are mixing together. Here, this is a three-chamber heart, and three-chamber heart, there is partial mixing. But here there is a 4-chamber heart in higher class of mammals and human being. We can see this. Here the lung circulation and the systemic circulation, these bloods are totally unmixed. As far as thermoregulation is concerned, so we can see the thermoregulation has also changed like this. Here, the thermoregulation of fishes, etc., they will be ectotherm. They will depend on the mercy of the environment. Here it is in between. Here we have got reptiles, etc. It is in between, and here the animal, it has got the complete regulation over its temperature, body temperature. Of course, if the system is very acute, then the regulation will not work, as we can understand. Now, the cardiovascular system, I have not to tell much regarding the cardiovascular system. In human being, the cardiovascular system has got two kind of circulation. One is your pulmonary circulation and another is your systemic circulation. And there are different kind of valves, etc. So if we see, I mean, this is some sort of an animation of the heart. And these valves, they operate in such a way so that we have got unidirectional flow of blood. And if we see the functions of blood, one of the functions is to create the uniform temperature in the body. It is also to transport heat from one part of the body to another. Heat generation, there are different body parts where heat generation takes place, but liver is one of them where a good amount of heat is generated, and it is transported by blood. Again, at the periphery, wherever we are getting thermal communication with the environment, there also blood plays a very important role. So that is there. And if this blood circulation is then somehow there is a problem in blood circulation due to some problem in the heart or in the heart valve, etc. So what will be its effect on thermal regulation? That is what we will discuss sometime to some extent. So cardiovascular diseases which can give some sort of problems in circulation, it will give primarily the problem, but again, that problem will be transferred to thermoregulation. So these are the things: the congestive heart disease, valvular stenosis, and aortic stenosis. So all these things, they give problem in case of thermoregulation. But we do not have much time. We will talk about only aortic stenosis out of these many cases. So aortic stenosis, if there is aortic stenosis, then what will happen? The aortic valve will not open properly and will not close properly. It is the healthy aortic valve. We can see how it is opening and closing. But in case of aortic stenosis, it will not open or close properly, which will increase the afterload of the heart. These are some sort of cardiac pressure and volume stress. I mean, just for common, I mean, our appreciation, I have put it. So normally the pressure, which is the aortic pressure, that is highest pressure is 120 millimeter of Hg, and the LVP, that means left ventricle pressure, that also peak matches with it, that is 120. And then we can get left atrium pressure, that is also there, and how the volume changes. And with this, what is the pressure and volume stress? This is for a normal heart. As the abnormality grows, then this this diagram, that will be lopsided. Okay, and some of these abnormalities we are going to see as we proceed. Now, as human body, if we consider it as a thermal system, the heat balance equation or energy balance equation is like this. the generalized metabolic heat balance equation for the whole body as well as a particular part of the body can be written as S. S is the time-dependent heat storage. Then M is the metabolic heat generation. E is the evaporative and respiratory heat loss. So this comes from sweating and respiration. When we exhale, then some amount of water vapor also goes out of our nose. And Q is the net heat flow to and from the neighboring part of the body or from the environment. C, that is the convective and radiative heat loss and gain. And W is the work done. Then Q and C, that could be positive and negative depending on the situation. So I have shown the general case that is positive. Based on this, the human body that can be idealized because the human body is so complex. We cannot take each and every part of the human body and do some sort of thermal analysis. So it can be idealized like that. There is a core which generally maintains its temperature. Then there is muscle, then there is fat, and then there is skin. Now, what happens that every layer that has got some sort of mass, some sort of density, volume, specific heat, and thermal conductivity. Now, the mass will vary from person to person. We have taken a specific case so that validation can be done. If we do some thermoregulation model, some validation can be done. So that way we have taken the mass. Other things are, they vary within a range. We have picked up the value from the literature. Now, for each and every layer, we can write down the energy balance equation and how it is changing with time. For core, we can write, this is the heat transfer to the core. This is due to respiration because lung is there within the core. This is kind of metabolic heat, and this is heat transfer due to blood flow. Similarly, we have written for muscle layer, we have written for fat layer, we have written for skin layer. In the skin layer, it is coming for environment, something is coming from the inner layer, then evaporation due to sweating is there, metabolic heat generation is there, and due to blood flow, whatever heat can come to the skin, that is there. Can come to the skin or go away from the skin. So that is there. So these are simple equations, but they are time-dependent equations, so that if there is a change in the environmental temperature, we can find out how the temperature of different part of the body will change. So this is so far the heat balance of the body is concerned. And then some of these things we have to calculate through some sort of correlations. So those correlations have also been provided. Particularly blood flow, how it will vary in different layer, and particularly in the skin, how the blood flow will vary. It will depend on the body surface area. It will depend on the core and skin temperature. So those functions have been picked up from literature. Now, once we have done the thermal model, then analytical model of cardiovascular system, because we want to see some sort of a combination. So what we have done, we have done the systemic circulation we have modeled only with the left ventricle, and then with the left ventricle the blood is coming to the aorta, there is aortic valve, so the valve has been considered and the valve resistance has been considered. Then the compliance of the aorta, that has been considered, compliant of the systemic veins, that has been considered. Then it goes to the left atrium, the atrium compliance, that has also been considered, and mitral valve and mitral valve resistance, that has been considered. So basically, it is a time-dependent model, and we have used Simulink for this model. So we have got certain differential equation which is coming from energy balance, and we have got a Simulink based model which has got compliance, which has got resistance, which has got some sort of actuator, etc. So these two models are now combined together. So from the bioheat equation, we take the thermoregulation model. So what kind of regulation is going on or necessary that can enter in our total modeling platform. And then cardiac output from skin blood flow we can calculate from the bioheat equation because a different layer we have considered. From here, we will get the vascular resistance. This will be fed to the Simulink model of cardiovascular system. So either it will be in the normal operating condition or in the disease condition. So its output will go to the bioheat condition, bioheat equation. And with this coupling, we will be able to get the temperature at different parts of the body, and also we will be able to get the blood flow rate through different layers of the body. Now, some results we can see. The first one is for a normal heart, and here we have also validated it with some sort of result who has considered a different model and no cardiovascular model, only temperature model of the body. And we can see that they have considered for two different ambient temperature. One is 29 degrees Celsius and 26 degrees Celsius. And it gives a very good matching. Actually, temperature, we have exaggerated the scale, so the matching is good. And then we are considering that, let's say, initially ambient was at 26 degrees Celsius. Then the ambient temperature is reduced to 20 degrees Celsius. Then it is increased to 30 degrees Celsius, and then it is increased to 40 degrees Celsius. Some kind of an imaginary thermal cycle. So here what I can see that the core temperature, even though there is almost 20 degrees Celsius temperature difference, core temperature remains constant. Because we have considered all the thermoregulations, means as far as possible in our model. The skin temperature that falls and up to this point. After that, the ambient temperature is increasing, the skin temperature is also increasing. Then after that, again, the ambient temperature is kept at 40 degrees Celsius. So here, what is happening to the skin temperature? Initially, it is increasing, but after that, it remains more or less constant because from around 25 degrees Celsius, sweating becomes operative or sweating takes place. And after certain rise of temperature, only there is maximum heat transfer from the body by sweating. The skin temperature does not change. So this is also, conforming with the physiological condition. So variation of cardiac output under different ambient condition. So here the cardiac output, as we have got the cardiac model, we can see that initially when the temperature is 20 degrees Celsius, which is a low temperature, then the cardiac output falls. We do not need that much of blood flow. Then when it is kept at constant at 30 degrees Celsius, the cardiac output increases. We need more blood flow below the skin to dissipate the heat. And then the sweating starts and the cardiac output increases. But after some time, there is a limitation. The cardiac output will remain constant, more or less constant, or asymptotically it will become constant. Cardiac output means the blood flow rate in liter per minute. That is our cardiac output. So beyond that, if we continue, or beyond that, if our temperature increases further, then what we will get? We will get temperature rise in the core, and some sort of a drastic failure in the circulation system. But we have not carried our simulation after beyond this point. The simple reason is that here many kind of biochemical equations and the biological operation that becomes important, which cannot be taken care of by our mechanistic model. So we have stopped over here. Now, the cardiac output, that depends on two things. One is your heart rate and another is your stroke volume of the heart. When there is a change in the cardiac output, so there is change either in both or any one of them. So our model is also capable of picking up whether there is how much change is there in the stroke volume and how much change is there in the heart rate, because from our thermal model, we could get the blood flow rate at different layers, and from there we can also get the resistance of different heart valve. So putting that in the cardiovascular model, we can separate out what will be this change in stroke volume and what will be the change in the heart rate. So here, do I have time or should we try to, hello? Do I have, I need some, let's say 5 to 7 minutes time to.
Yes, sir, please continue.
Okay, okay. So here quite a few interesting things we can see. The thermal cycle, which I have told that for certain period we are having 20 degrees Celsius, then 30 degrees Celsius, then 40 degrees Celsius. Skin temperature changes like this. This I have shown earlier. Only for comparison I have. Then it's here. Then it further rise, but the further rise will be constrained as sweating starts. After that, if we consider the sensible heat transfer with ambient, then when there is low temperature 20 degrees Celsius, then there will be heat transfer. Outside temperature is less, so there will be heat transfer from the body, and then then what will happen that heat transfer direction will change. Here we can see that this is the 0 level, and after that the direction will change. But that is also having some sort of a limitation, because we can see the rate of change of sweating or rate of heat transfer due to sweating, that is reducing. Okay, and as I have already told that if we go for a higher degree of outside temperature, or we continue at 40 degree, so a physiological condition that when somebody has sweated profusely, that will take place, and sweating will not be very effective for transferring heat from the body. So that is some sort of a crisis. Now, if we go to the next slide, here what we can see that under ailing heart condition, if there is that left ventricular ejection fraction, if there is reduction in the left ventricular ejection fraction, surprising what we can see that core temperature and skin temperature does not change much, because there are other regulatory mechanism in the body which will prevent the changing temperature. What will happen on the other hand, we will have skin blood flow rate that will drop. Rate drops with the reduced left ventricular ejection fraction, which affects thermoregulation. So that is there, and again, as I have told, if this condition continues for long, or the ambient condition become more than 50 degrees, 60 degrees, then we will have some sort of a crisis for the thermoregulation. Finally, I come to this. Here, this is another ailing heart condition where there is stenosis. So first we have considered healthy heart, where the LVP means left ventricular pressure is 120 millimeter of Hg. And we are considering two conditions. One is ambient atmospheric temperature, and another is 40°C temperature. So if there is healthy heart condition, in both the cases, we will have aortic pressure same. Mild stenosis, there also we will have more or less same pressure pulse from the aortic pressure, but obviously the left ventricular pressure will increase. It has increased up to 140. Here, the left ventricular pressure that will increase up to 160, but still here we will have the temperature effect almost not felt in the aortic pressure. In the last case, where there is severe aortic stenosis and the left ventricular pressure is more than 180 or so, here what we can see, the temperature effect and the aortic pressure has fallen drastically. And this fall, it can give a condition of like syncope. That means the body, its inbuilt mechanism is there. It does not allow the body to endure the pain for a long period of time. So some sort of senselessness or some sort of blackout that may come in this condition. So this is a combination of high heat stress plus high severe stenosis condition. So here we can get this kind of a. So all these things are obtained from our simulation. And it is also reported in medical literature that these kind of conditions can be seen. Direct comparison cannot be done because these kind of tests have not been made. But whatever we have observed during our simulation, that has also been reported in different medical journals. Finally, I like to end with this slide, this information. This is very interesting and very recent one. We are familiar or we know regarding sauna bath, which is very common in Finland. In Japan also some kind of sauna bath is there. In other places in advanced countries, sauna bath is there. Sauna bath is bath by steam or bath by hot air or exposure of human body to that for a prolonged period of time and then cooling the body. Now, when sauna bath is taking place, I mean, or somebody is taking sauna bath, so what is happening that it needs increasing cardiac output because the body has to be cooled. But this, let's say for 45 minutes to 1 hour sauna bath somebody is taking, there will be rise in the core temperature, 37 degrees to 39 degrees Celsius. It is not as high that it can create some sort of a permanent damage to the body, but it will create a heat stress which will give increased cardiac output and it will give increased heart rate. 60 to even up to 150, that increase can be there. Over the years, people have studied it and it has been found that there is an increased heart rate. Now, if this is done repeatedly, let's say somebody is taking this sauna bath 2 times, 3 times a week, then what will happen? The body, there will be some physical change. Then it will give you improved left ventricular function. That is one way it will change the heart function and it will have higher heart rate, etc. Improved resting blood pressure that it will give. Systole and diastole, there will be also some sort of improvement. At the same time, it will improve the vascular compliance. That means the vessels, blood vessels that will become of, or that will inflate, that will become of larger diameter. Even the endothelial vessel, that will also increase its diameter. And these are permanent change. So as if somebody has taken some sort of cardio exercise for long, or aerobic exercise for long, so that the body conditions have changed and now we can have some sort of protection against heart disease and increased longevity. So this has been seen that if somebody takes sauna bath very regularly, over different group of people it has been tested, then the risk of heart attack that reduces 30 to 35%, and the longevity or lifespan that increases. So this shows a very direct relationship between your thermoregulation and cardiovascular system. Okay, with this, I like to end my talk. Some summary I like to make quickly. The model of human thermoregulation can predict the variation of skin and core temperature effectively, whatever simple model we have done for different ambient temperature. And it is observed that though the skin temperature varies over a large range, but the core temperature that remains constant 36 to 37 degrees Celsius. The combination of Simulink and the thermal model that gives a prima facie picture of the nexus between cardiovascular system, cardiovascular circulation, and the thermoregulatory system. So this is kind of, so far we have not seen this approach in the literature. But one drawback of this, that unless the biological aspects, biochemical reactions, etc., are not taken into cognition, then this model will have only limited prediction capability, particularly at low temperature and at conditions of mild cardiovascular illness, it will be able to predict. It is also observed that reduction of cardiac output is mainly governed by steep decrease in the heart rate. So heart rate and stroke volume, these are the two input parameters, or rather two independent parameters. May not be totally independent, but the cardiac output depends on these two parameters, and our model could separately find out the effect of both of them. The investigation also shows that after approximately 30 minutes of heat stress of 40-degree ambient temperature, blood pressure of a patient with severe stenosis, aortic stenosis, will get reduced drastically and may cause CPO. So then heat stress for a person who is having the ailing heart, that is not very good, and that may create further problem in the physiological system, and something could be fatal also. Then finally, which we have not worked, but we have shown that by kind of controlled heat stress, one can even increase the capacity of the heart and increase the longevity of human. So that's all I wanted to present.
Okay, thank you, Professor Das. So this is an excellent lecture connecting that your thermodynamics heat transfer with that biological systems, particularly in human bodies. And I think now it is the high time to contribute something from the science and engineering to the biological science for the better treatment. So in that respect, this type of lecture or study is very useful. But still you have to go a lot. So now we can initiate that discussion. I mean, any queries, any discussions that we can initiate now.
Yeah, I will be happy to or try to answer, because as I have told that there is a very strong biological aspect and endocrinological aspect. So those things we do not know. Some literature discusses that, but we need time to understand, and we need time to amalgamate them with our mechanistic kind of model. Either it is a heat transfer model or a control model.
Okay, I think Machudha is the right person to initiate the discussion. So we can start. You can start.
I am absolutely dazzled. I have not come across such absolutely wonderful, beautiful lecture in the simplest of language, which can be understood by uninitiated people like us who knows only mechanical engineering. But our body is a great example of how the mechanical engineering laws of thermodynamics holds very clearly their grip over the functioning of the human body. Such kind of lecture, Professor Das, I have never heard in my life, and I cannot express my amazement and my praise for such beautiful appreciation, beautiful presentation. I hope this is the beginning of the story of various biological functions. You have handled one, but there'll be plenty of others. And this particular part, maybe 30 or 40 of your students can work further in the various aspects of the job. Thank you, Professor Das.
Okay,
It was amazing for me.
actually, if I like to again share with you, it is like this that I mean tremendous activities are going on in the field of biology, in the field of medical science and biology, and what I believe that so many artificial organs have come, and means in coming years there will be many artificial organs. Maybe in human body, there will be systems with some sort of a chip, some sort of control from inside and maybe integrated with outside also. And the longevity could be increased, the quality of life could be increased to a very great extent. Many of the things are coming. I mean, at one point of time, heart used to be, one used to think that heart is some sort of a mystery. Even in the doctor's ethics, earlier days, it was told that do not touch the heart. I mean, it is a crime to touch the heart. Suppose somebody is doing some sort of a surgery, he can do surgery to other parts, but touching the heart, it was supposed to be a crime. So nowadays people are thinking in so many different ways to have some artificial heart, and it will come. It will come very soon. I mean, which can, I mean, already it has come and it will come.
One more statement, Professor Das, from me. Actually, this is a final frontier, if you can say. In our mechanical engineering, we have got other frontiers. We have solved various frontiers of physical sciences, but this is an ultimate frontier. So this we know better and better. And
No,
it's a great.
but problem is that this is not the frontier of mechanical engineers only. One has to work, means biochemical engineer and chemical engineer, materials engineer, electrical engineer. Everybody has to work, biologists. Everybody has to work together in a team. Then only things will come. And I mean,
Sir,
whatever has been done, that is by due to some group activity only.
sir,
Whatever small has been
single
done.
physical elements has all been touched by the engineering community, and they have been somehow solved or they have been categorized. But this is the final frontier in a sense I was telling. And of course, we have to attack the final frontier. Our knowledge base in various branches has to be used to know about it. Thank you, Professor. It was a pleasant thing for me.
Thank you for your kind words. I mean, I have tried to do only a small kind of simulation and some reading, nothing more than that.
Professor Das, this is Sham Ganguly. I got a question for you.
Yeah.
You have, by the way, I mean, I totally agree with Achyuta that you did an excellent job. I was a little bit scared that I won't be able to follow your presentation having no medical background whatsoever. But you made it in terms of mechanical engineering, and thank you for that. But, I was thinking that cardiologists and doctors, they tend to think, and correct me if I'm wrong, that they know all more about hearts than mechanical engineering do. So, how is your research and your output taken by the medical community, or are you presenting it to the medical community, and
Uh,
how are they reacting to it?
Thank you for this question. Actually, this is a very I mean, it is a kind of side work, but for last 2-3 years, we were working on some sort of heart-related prosthetics. So it is called LVAD, left ventricular assist device, which is some sort of a pump which will not replace the heart, but it will remain and it will pump the blood. Generally, left side becomes weak, so it will pump the blood, and it is a mechanical pump. I mean, mechanical pump driven by battery. The power line will come outside the body, and person will have the battery. And people told, actually, people means stalwarts. Like in our country, one of the stalwart is Dr. Devi Shetty. We visited him, and he told that this could be the future answer for heart problem. And the heart problem, the golden solution is replacement of heart, okay, by a donor heart. But the number of donor heart available, that is so small that one has to go for this artificial kind of thing. And I mean, whenever I have gone to any doctor and talked about this, everybody has shown interest. Only thing is that maybe that is my fault, or it is in our country things move like this. That after the initial work, the next phase where we need a lot of support. So somehow due to COVID, etc., everything put together. We are still trying. So, but the next level of support, it is very difficult to get. So next level of support means where we can, whatever we have developed, we can test it in the laboratory, can we test it in animals, etc. So that kind of support, it is difficult to get. But there is lot of interest from the doctors. And even in Calcutta, etc., doctors from Calcutta, they are telling that, well, simulations are very important because two human beings are not identical. By simulation, before operation, if we can know something, and that's how we can select the prosthetic or plan the operation in a right manner, that would be a great help. So even this has been told.
Great answer.
Even this has been told by doctors. So there are interest, but I do not know how to go about it because it seems that lot of problems are there ahead of us.
May I suggest one thing? Since in the IIT Kharagpur, you have that biomedical system, so nobody will permit, no patient will permit a mechanical engineer to touch their body. But when you have the medical profession along with you,
yeah, means
then
whatever
they
we
will
have done
permit.
in the laboratory, now we have to go next phase, means doctor should be, I mean, more than us, the doctor should be involved.
Yes, yes.
Yeah. That is true. There are many things, ethical questions and all these things are there. It is not like mechanical engineering, pure mechanical engineering research. So there are many things.
But this is fascinating.
This is
Fascinating.
fascinating. Biology is fascinating.
Truly cross-functional.
Prashant, can I ask something?
Sir?
Yes.
Can I ask something?
Professor Mollik, sir, bolun.
Yeah, I am totally ignorant about cardiovascular system, fluid mechanics, heat transfer, and thermodynamics.
No,
So
no,
my
no, no.
questions can be
Please.
very idiotic. You can
No, please,
try to
please.
say so. One is repetitive long sauna bath and heat stroke. Where is the basic difference? You said sauna bath is good for cardiovascular system.
Yeah. And there are a lot of papers now. Very recently, a lot of papers are coming. Of course, earlier also it was there. Sir, first thing is that sauna bath is controlled. Heat stroke is not controlled. Okay. Sauna bath is designed in such a way so that human beings are getting stress, but after that it is all right. So that's how. Otherwise, why you will take sauna bath?
But the heat stroke, you may get it, I may not get it, though we are equally exposed. So there is something basically to the,
that is true.
sample.
That is true. That is true. That heat stroke is uncontrolled, and heat stroke, well, it will also depend on person. So it may be, I am not sure, but it could be that sauna bath also 2%, 1% may feel it very.
No, is there any basic difference in the mechanism of heat transfer that causes this? That was my question. heat being transferred both in the heat stroke and also in the sauna bath.
Yeah. Only
But
thing
through
is that
steam
when
and
you
through direct
take,
radiation. So
when you
that is
take,
the difference.
no, no, sauna bath is by convection, not by radiation.
Just I'm saying, but heat stroke
Heat stroke
is
is
by
primarily
radiation,
by
right?
No,
Mostly.
what I am telling is like this, that sauna bath, I have not taken sauna bath any time.
I only take hot water baths. Sauna bath I don't take.
No, no. I have to take it. I mean, I have to do more literature search. Sauna bath, you are going prepared. Means you have removed your clothing to the bare minimum, and I do not know whether the temperature rises gradually or not. Maybe there the temperature rises gradually.
Actually, normally there are heated stones and water comes there and it becomes steam, and that is
It
how
becomes
the
steam. It becomes steam, and then that is coming, and there are dry sauna bath also. Okay, so both are there. Whatever you have told is wet sauna bath, and there is also something called dry sauna bath.
dry sauna bath.
Okay, okay, but it is by convection.
So basic thing is the heat stroke is uncontrolled, sauna bath is controlled. So that
Sauna bath is controlled. That is another thing. Another thing is there, that what they are telling, that heat stroke you are getting once, and then you are afraid, and then you are ill. I mean, then you are sick, and then I mean, second time you are not having it. But sauna bath, what they are telling, this sauna bath, somebody who is taking 2 to 3 times per week, 3 times per week, then for that person the heart
rate will be
condition is improved and longevity is improved. So it is.
Okay. The second question I had is,
Sir,
what is
just
cold
one more sentence. Let me complete it. It has been told in these papers that it is like this, that Noel, how can I give the example, that somebody is exposed to a lower grade of poison repeated times, and it is known that somebody gained some sort
level
of
the resistance against poison, right?
some sort of immunity, and this we have seen even during COVID. We have seen
না
that.
না আফিম খেয়ে আমার দিদিমা বেঁচে গেছিলেন। তাকে চোর ধূত্র ফুলে বিষ খাইয়েছিল, কিন্তু আফিম খেতেন বলে she was saved.
হ্যাঁ,
I know
তো
it.
আমি জানি এই ধরনের গল্প আছে, এবং আমাদের এমনকি বিশ্বকন্যা সে ধরনের গল্প আছে। তো গল্পের দিকে না গেলেও দিস ইজ এ প্রুভেন থিং দ্যাট ইভেন আওয়ার ভ্যাকসিন।
So vaccine, you call your malaria treatment, that Cinconagach, that thing.
Belladonna is there.
So that is there, that if you take a controlled lower dose, so probably you gain some sort of strength to
Yes.
or your body, some sort of changes are there, which is good.
And second thing is, what is cold sweat? Sometimes there is no heat, even in air conditioned room. There is some due to internal problems.
Due to internal problem, there is cold sweat.
A huge amount of sweat is all.
Yeah. Particularly the persons who are having some sort of illness. Maybe you are having some sort of a severe illness, and then you are trying to I mean, go upward in a staircase. So some sort of exertion is there, but the outside temperature is not very high. Even then you can have sweating. Okay, and this is good. See, the explanation is like this. Again, the explanation is like this, that the sweating is not fully dependent on temperature.
Right.
It is also some sort of endocrinal activities are there, and I mean, when this kind of things are there, means somebody who is weak, who is not well, but trying to raise some stairs, etc. So then this endocrinal activity will switch on, and this cold sweat will be there. Again,
I myself had it 7 years back in an air conditioned room. My friends got worried that I might have got a heart attack because huge profuse amount of sweating. My vest and everything became wet.
No, then before heart attack also, temperature may not be that high. People can have cold sweat.
Thank you, Prashant. Thank you. Very
Thank you.
nice lecture. That is, I mean, I am not the person to say that. We all know you.
No,
Know you.
no, no, no. No, sir. Thank you. Thank you. আপনি আসবেন আমি তো ভাবতে পারিনি।
না না আমি তোমার জন্য এসেছি এত চেষ্টা করে
না,
আজকে আমার
ভাবার
কানেকশন
থাকলে
হচ্ছিল
কিন্তু
না
ভয় পেয়ে যেতাম আমি আগে থেকে একটু
আমি আমার বন্ধু মিস্টার পালিতকেও বলেছি যে প্রশান্তর লেকচার ইট উইল বি শোনার মতো প্লিজ এসো
Thank you, sir.
Sir,
Thank
one
you.
small query. In your simulation, particularly when you are simulating the cardiac responses to high heat or high cold. So in both the situations, are you considering a particular activity for the human body?
No,
Means how the human activity might change that heart rate also?
no. So these are the point. Means what we have done is very simple thing. So even when people are exercising and then there is temperature, etc., people can look into
So
those things.
this has to be taken care of, right?
This has to
Particularly
be
at the-
taken care of.
I have one question regarding the simulation. So our conventional simulation, we normally consider these equations like your continuity, Navier strokes, and energy. For this particular case, what is happening in the human body, do we consider any other sort of equations?
No, actually, what is done, I mean, it can be done whatever we have, whatever you have told. At least if we want to see the human body as a mechanistic system, mechanical system, and all the physiological actions are some sort of mechanistic actions. So then one can simulate it. But only what we have done, we have used the Simulink, where dynamic simulation can be done very well if you can identify some sort of a lump parameter having some resistance, some sort of capacitance, some sort of inductance, etc. Then you can have this simulation easily because that software is available. So we have used that.
So one more thing is that
this we have used for heat transfer. Those are simple equation, those differential equation we have done, and there is data transfer between these two.
you know, one more thing is that so when you are suddenly exposed to some relatively high temperature or low temperature, we feel very uncomfortable. But after some time,
acclimatization takes place.
Yeah, it is. So is what thermodynamic processes takes place inside the body?
No, this is biological process.
Okay.
This is not thermodynamical process. This is biological process. To some extent, it could be mechanical process like your, as I have told, vasodilation and vasoconstriction, those kind of things that can be there. But these are biological process, and unfortunately, nobody has looked into the biological processes and put it some sort of, I mean, maybe some chemical equations, etc., giving some chemical equation, etc. So that is one thing we should do. Otherwise, we will be just scratching on the surface. Maybe we will have a couple of paper, etc., but not much.
So can you not identify some thermodynamic process with that biological process?
If it is thermodynamics also, by us, it cannot be handled unless we also increase our knowledge, because it will be chemical thermodynamics kind of a thing. Because, see, what I have heard from my colleagues, that unfolding and folding of protein, there also some thermodynamics is involved. But, I mean, we are not aware of that kind of thermodynamics. Reaction kinetics, those kind of things will come into picture.
So our student can participate because you are studying now, you know, thermodynamics and heat transfer particularly.
And mentioning also in RAC also we have a chapter, the human body mechanism, how we respond to the changes
we have
in
also
environment.
studied some sort of biology in school level. So students, you can ask your questions because you won't get such a person in future easily. Okay.
Sir, there is one question. I am Rishiraj Ranjan, sir. There is one question. Am I audible?
Yeah, you are audible.
Not visible.
Yes, sir. Sir, in thermoregulation model, what you are referring means core. You are just telling that core means. Are you referring like bones or something?
Are you referring?
Bones.
Actually, core temperature means temperature of the skeletal structure, temperature of heart, lung, then liver, kidney, those kind of things, and brain also. though the brain is not in the core. So these temperatures, generally, the human body does not allow fluctuation. And that fluctuation is very less, 0.5 degree fluctuation. In general, there is only 0.5 degree fluctuation. During abnormal condition, fever is one abnormal condition. So during fever, it goes up. Or as I have told that sonabath, etc., that slowly your core temperature is being raised. So otherwise, there is no change in the core temperature.
That is the, I would say, surprise of nature, that so many chemical reaction can take place in such a little temperature range.
Yeah.
Rather to maintain the core at that within that range.
Huge temperature range is necessary.
Yeah, definitely. So definitely the human body has done, during evolution that, okay, I will have such chemicals, etc. We will have within a narrow range these important reaction, and these chemicals also, that means all the hormones, etc. are chemicals. So they will also not change. And there, if there is any change, there will be some sort of a change in the structure of protein, and it will take care of certain functions.
Yes.
So,
Like
that is
probably like air conditioning, we could say that there is a body conditioning mechanism in us.
Yeah, definitely body conditioning mechanism. And it is only temperature we are telling, that pH balance, then sodium potassium balance. So all these things, and balance of liquid. So many things are there. And whenever we are trying for our own convenience to model something partially, we are getting only the partial picture.
May I ask a question, please? If it is
Yeah.
okay.
Yes.
Lalit here. Am I audible?
Yeah, sir.
Okay. Dr. Das, first, again, let me repeat that for this illuminating lecture. And I may say that with my background, I could not understand much, but at least it reassured me on 2 points. First is that, say, reptiles, etc., they have to depend on sun so as to get their body temperature control. That way we are lucky. We have got our own mechanism to control our own temperature. That is very reassuring, number one. Number two is, talked about frostbite. Now, okay, at least this much I came to know. Frostbite, I am sacrificing something, but that is for a greater good. That is, my heart is being saved. So that is very
being saved by losing a few fingers.
Yeah, that means I am losing a few things, but I am saving something much more important.
And those are, you are losing only the exterior of the limbs.
The exterior of the limbs.
Correct.
Absolutely nothing internal. And the maximum distance possible from the core.
Correct.
Yeah, actually, what has been seen, fingers of hand and leg, and sometimes ear, etc.
Yeah.
Yeah.
It becomes totally hard, brittle.
And last thing, I mean, it has already been said your initiative is very laudable, but as you said, initiatives, sometimes they don't see the future action or the supporting action. So I wish you that your initiative meets with some finitiative.
Thank you, sir, for your please.
So
we are trying, but let us see.
Lecture.
And actually, this pandemic has made many things topsy-turvy. That is also one.
Yeah. Thank you.
Okay. Thank you.
Yeah.
Thank you.
Well,
Thank you for
Vijayendra, if there is if there is no more questions, I have one responsibility on behalf of the department and on behalf of the Centenary Celebration Committee. Yes, Vidut?
Kamalda was trying to say something.
Oh, yes, Kamalda? Please go ahead with your queries.
Thank you. Can you hear me?
Yes, you are audible.
My voice is my voice is a little cracked, but let me make general comments. Number one is that I absolutely agree with Ochita. It's a wonderful presentation. Now, I'm looking at it as a system level, and your presentation tells that human body is adaptable. our system regulation is very interesting. Now, people have talked about a lot about making a body more robust using physical exercise, mechanical loads. But this is the first time I heard, and wonderfully, that yes, just like a mechanical system, you can regulate adaptive material through temperature regulation also, not just mechanical loads. So that is very interesting. That gets to my personal interest. I have a bad name in my family because I take typically 30 hours of shower, and after I take it, nobody can go to the bathroom because the temperature is so high. Okay? I take very high temperature, and I love it. And now I can tell all my family people I am doing the right thing. Rather than running around, I am going to the shower, take a half an hour high temperature shower. I am basically strengthening my aerobic system. By the way, I just found the other day that I have got aerobic restenosis. Okay, so I think I'm doing the right thing. But coming back to another issue, I think it's a validation of a point. I think this is definitely a area you can think about, see what we can be done. If people talk about running around mechanical exercise, but why not thermal exercise? That's the point you can think about. Number two is that I think this is really interesting for your model to use it in extraplanetary inhabitants. Like when people go to Mars or Moon, clothes are type of clothing, what kind of system you should devise, your simulation will be very wonderful too. Okay. And last but not the least is that you're absolutely right. Your data is extremely powerful, developing useful devices, artificial prosthetics for human body, where so far I know most of the work research has gone really on the mechanical aspect of it. Nobody looked from thermal aspect of it. Very few. So I think this is another area you can think of. At the end of the day, as Ochudha said, my friend Sham said, it is a wonderful lecture and even so simple, what I call deceptively simple. Really, fun. Thank you so much.
Yes.
Thank
Okay,
you, sir.
so
Thank you, sir. Thank you.
finally, we have to come to the end of this excellent session. So before that, I want to say that we are in constant touch with Professor Das because today morning, I think he has conducted one PhD Viva a few weeks back.
Yes.
But unfortunately, he is not able to come here due to this COVID situations. So I think in future, he will come for many occasions and our student can interact with them. So before closing that, I want to hand over to our HOD, Professor Sudeep Ghosh, to complete the formalities. Professor
Yes.
Ghosh.
Yes, thank you. On behalf of the department and on behalf of the Centenary Celebration Committee, let me thank our today's speaker, Professor Das, for this brilliant presentation and brilliant discussion. It's a wonderful thing. It's a nice thing and it's really stimulating. We have a certificate as a token of appreciation. The soft copy you can see here online. So this will be sending to Professor Das by email. We also have a hard copy of it along with a memento that we will hand over to Professor Das somewhere, sometime when he visits her, or maybe we'll send it to his Kharagpur address. Thank you, Professor Das, for this nice evening. I must also take this opportunity to thank our today's chair, Professor Bijan Mondol, for leading the session so nicely. And I must also thank our senior members of alumni, our students, and our members of faculty, members of Gabeshu. Anjanadi was also there. So thank you. Thank everybody. With that closing words, we would be coming to the end of this session.